Hello, our project is a novel approach for DSP controlled method for single phase induction heater. As we all know that induction heating is a non-contact heating method in which an electrically conducting material is heated using alternating magnetic fields. The industrial induction heating machines in existence today rely on human attention to keep the system secure and working. The frequency of operation is changed manually, thus resulting in overall decrease in the functioning speed and poor efficiency. Setting the timing parameters like on and off time is a complex task and cannot be achieved with high precision. The aim of this project is to develop a fully automated control system for monitoring of induction heating systems. Using the code for sine triangular modulation, a varying PWM is generated which is applied to the full edge bridge IGBT module so that it can provide an equivalent sine wave at the load. The feedback circuit of the control system helps in increasing the power efficiency of the system. Low pass filters and feedback circuit is implemented as algorithm in DSP which helps in reducing the losses and improves the reliability of the system. Now, let us take a look at the system level diagram. On startup, the system takes an input from a reference signal generator which provides a sinusoidal signal. The signal is then given to a signal conditioning block which generates a DC level shifted signal between 0 to 3.3 volts, which is fed to the DSP. The DSP algorithm now performs the signal conditioning if required. The algorithm eventually leads to the generation of gate pulses which are inputted to the buffer for isolation. These signals are given to the IGBT gate drivers which are connected to the full edge bridge IGBT module. The current through the load and the voltage across it are sensed and given to the signal conditioning block for scaling and level shifting. The condition signal is fed back to the DSP algorithm. The algorithm initially operates on the reference signal and then automatically switches to the feedback signal.
The criteria for selecting this DSP is firstly fast and floating point computation, secondly ADC for high frequency sampling. Port 60 and 61 of the GPIO on the development board is used for gate pulses output. One of the ADC channel is used for sensing load current which comes from the signal conditioning board. DSP is programmed in Flash for standalone applications. Now let us have a look at the algorithm. The sine wave is stored internally in the buffer which is done by internal harmonic oscillator or external function generator. This allows the whole system to set under ideal conditions. After some time, the algorithm switches itself to the sine wave produced by the load current. The triangular wave is generated having 50 kHz frequency. The comparator is implemented. When sine is greater than triangular wave, PWM goes high. When sine is less than triangular wave, PWM goes low. Thus, an SPWM pulse is produced. Another delayed version of SPWM pulse is produced. The subtraction of both the SPWM wave results in the voltage appearing at the terminals of the load. The RLC load is internally simulated. Reference power is set in the algorithm. Power across the load is calculated and passed through the low pass filter to give actual power. The comparison takes place between the reference and the actual power to produce the error signal. This signal is passed through the PI controller to produce feedback control signal, then multiplied with the sine wave and compared with the reference triangular wave, and thus the power is made constant. Hardware setup of our project. This is TMS 320F 28335 kit. This is one of the gate pulse produced using the DSP which will be given to the gate drivers. Now I will explain the signal conditioning block. One of the TL072 op-amp is being used for attenuating and DC shifting the sensed voltage across the load and bringing it to a scale of 0 to 3.3 volts, while the second TL072 op-amp is being used for amplifying and DC shifting the sensed current through the load and bringing it to a scale of 0 to 3.3 volts. The third op-amp is used for wave shaping if required in future for zero voltage sensing. This section of the circuit is the rectifier and voltage regulator consisting of UA7815 circuit and UA7915 circuit, which are TIICs used for producing plus 15 and minus 15 volts. This is the current sensor output which is connected here. This is the step down transformer input which is connected here. The voltage across the load is connected here. The output is obtained here, which goes to the DSP connected to the ADC channels. The DSP algorithm will operate on these signals and correspondingly produce gate pulses, making it a closed loop system.
Here we have plotted the results obtained by execution of a code on a DSP using the graph plotting tool of Code Composer Studio. Here you can see that the output current is near sinusoidal due to the resonant operation. Here we had set the reference power as 3 kilowatts, and as seen in this graph we can see that the power is fluctuating between 2950 watts to 3050 watts, which is approximately near 3 kilowatts. This graph shows the variation in the value of control signal, that is the feedback control signal. As seen, whenever the power increases beyond the reference value, the value of the control signal goes on reducing. If it falls below its reference value, it starts increasing again.
The advantages of proposed system is that the external noise is reduced due to the digitalization of analog circuitry used in conventional systems. Also, the noise due to the temperature variation is reduced. Thus, the proposed system is reliable and efficient. The system also provides flexibility, as for any changes we just need to change the code. Thus, it is a versatile system for various applications. Unfortunately, the system is not tested with induction heating load due to untimed delivery of required hardware including IGBT and the coil. We thank TI Innovation Challenge for encouraging us to work on industry level project. We would also like to thank our mentor Dr. Y.S. Rao for his constant support and guidance. Thank you very much.